Welcome to Complex Analysis. Today, we are going to explore one of the most beautiful, strict, and fascinating requirements in all of higher mathematics: the conditions for a complex function to be differentiable. If you have ever wondered how calculus works when numbers live in two dimensions instead of just a flat line, you are in the right place. We will build this understanding from the ground up. To understand why complex differentiability is so special, imagine standing on a hill. In standard calculus, you can only step left or right along a straight line to check the slope. But in the complex plane, you are on a flat two-dimensional surface. You can approach your exact location from an infinite number of directions: north, south, east, west, or even spiraling inward. For a complex function to have a well-defined derivative, the slope you calculate must be exactly the same no matter which of those infinite paths you take. This massive requirement brings us to the formal mathematical definition of a complex derivative. Conceptually, it looks just like standard calculus, but the variables live in two dimensions. The symbol f prime of z0 represents the complex derivative. The numerator is the tiny change in the function's output, and the denominator, delta z, is the tiny change in the input. As delta z shrinks to 0, we look for a stable ratio. But remember, delta z is a complex number. It can shrink to 0 along any path. If the final limit gives different answers depending on the path, the derivative does not exist. Now that we know the derivative must be identical from all paths, how do we actually test this? We break our complex function into its real and imaginary parts. Any complex input z can be written as x plus iy. Similarly, the function's output can be split into a real number function u and an imaginary number function v. Both u and v depend on the real coordinates x and y. By splitting the function this way, we turn one complex equation into two real number equations, allowing us to use standard two-dimensional calculus to analyze different paths. Before we look at the mathematical conditions, let us visualize these paths. On screen, you see a complex plane with a specific point z0. The green line represents approaching along a diagonal. The purple spiral shows a complex inward path. But the most important paths for our calculations are the horizontal red arrow, where only x changes, and the vertical blue arrow, where only y changes. For the function to be differentiable at z0, the mathematical slope calculated along the red path must perfectly match the slope calculated along the blue path, and indeed all other paths. This brings us to the absolute bare minimum requirement for a complex function to be differentiable: the Cauchy-Riemann equations. These equations guarantee that the slope from the horizontal path matches the slope from the vertical path. The first equation states that the partial derivative of u with respect to x must exactly equal the partial derivative of v with respect to y. The second equation states that the partial derivative of u with respect to y must be the exact opposite of the partial derivative of v with respect to x. If a function fails these matching rules even slightly, it cannot be differentiable. We must be careful here. Satisfying the Cauchy-Riemann equations is only a necessary condition. It is required, but not always enough on its own. To be absolutely certain that the function is differentiable, we need a sufficient condition. The sufficient condition states that the function must satisfy the Cauchy-Riemann equations, and all four of those partial derivatives must be continuous. Continuous simply means the derivatives flow smoothly without any sudden jumps or infinite spikes. If they match and are continuous, we are completely guaranteed that the complex function is differentiable. Let us see this in action with a concrete example. We want to determine if the complex function f of z equals z squared is differentiable, and if so, find its derivative. First, we replace z with its rectangular form, x plus iy. We then expand the square using standard binomial algebra rules. Remembering that the imaginary unit I squared equals -1, we group the terms to separate the real part from the imaginary part. This gives us u equals x squared minus y squared and v equals 2xy. Continuing with our separated functions, we now calculate the 4 partial derivatives to check our conditions. We check how the real part u changes with respect to x, giving 2x. The imaginary part v changing with respect to y also gives 2x. These match perfectly. Next, we check u with respect to y, giving -2y, and v with respect to x gives +2y. The first is the exact negative of the second, which is exactly what the second Cauchy-Riemann equation requires. Because our partial derivatives are simple polynomials, they are smooth and continuous everywhere in the complex plane. Since they satisfy the Cauchy-Riemann equations and are continuous at every coordinate, the function is differentiable everywhere. We can write its derivative using the horizontal path formula, which simplifies beautifully back to 2z. This confirms that the standard power rule from real calculus works for this complex polynomial. Now let us investigate a very different function. F of z equals the squared magnitude of z. The magnitude is the distance from the origin, so the squared magnitude is simply x squared plus y squared. Because this output is a pure real number representing distance, there is absolutely no imaginary component. We can explicitly write the real part u as x squared plus y squared and the imaginary part v as exactly 0. We move on to calculate the partial derivatives. The derivative of u with respect to x is 2x, while the derivative of v with respect to y is 0. For the first Cauchy-Riemann equation to hold, 2x must equal 0, which only happens if x is 0. Similarly, the derivative of u with respect to y is 2y, and v with respect to x is 0. The second equation requires 2y to equal -0, meaning y must also be 0. For this complex function to be differentiable, both Cauchy-Riemann equations must be satisfied at the exact same time. As our step-by-step calculations show, this simultaneous agreement only happens when both x and y are exactly 0. Therefore, this function is only differentiable at the exact origin of the complex plane. If you step even a microscopic fraction of a millimeter away from the origin, the equations fail, and the complex derivative instantly ceases to exist. This perfectly illustrates how strict these conditions truly are. Now that we have successfully used the Cauchy-Riemann equations, let us understand exactly where they come from by deriving them step by step. We start by testing the derivative limit by approaching the point purely along the horizontal axis. Here, we only change the real part by a tiny amount, delta x, keeping the imaginary part completely unchanged, so delta y is 0. Plugging this horizontal change into our limit definition, we separate the real and imaginary parts. As delta x shrinks to 0, this simply becomes the standard partial derivatives of u and v with respect to x. This gives us our first expression for the complex derivative. Next, we test the limit by approaching the point purely along the vertical axis. This time, we hold the real part perfectly still, so delta x is 0, and our complex change is purely imaginary, written as I times delta y. When we plug this into the limit definition, the I in the denominator interacts with the I in the numerator. Because dividing by I is the exact same as multiplying by -I, the real and imaginary parts swap their roles slightly. As delta y shrinks to 0, we get our complex derivative calculated from the vertical path, giving us our second expression. This brings us to the final step of our derivation. Remember our golden rule from the very beginning? For the function to be differentiable, the slope must be identical from every possible direction. Therefore, the mathematical result from the horizontal path must perfectly equal the result from the vertical path. By setting the real parts equal to each other and the imaginary parts equal to each other, we directly obtain the Cauchy-Riemann equations. This proves exactly why these specific matching rules are the absolute bare minimum requirement for complex differentiability. The math must agree from all angles, and this derivation shows exactly how that agreement is enforced. You might wonder why this strict mathematical condition matters in the real world. It turns out that many physical phenomena naturally obey the Cauchy-Riemann equations without us forcing them to. The smooth flow of water around an obstacle, the invisible lines of force in an electric field, and the steady flow of heat all follow these exact rules. When a function is complex differentiable over a whole region, it is called analytic, unlocking powerful tools that engineers use to design airplane wings and analyze electromagnetic waves. Let us summarize what we have learned. Differentiability in the complex plane is incredibly demanding because the slope must agree from infinite approach paths. This synchronization is governed by the Cauchy-Riemann equations, which dictate exactly how the real and imaginary partial derivatives must match. When a function satisfies these equations and has continuous derivatives, it is officially differentiable. You have now mastered the foundational conditions that open the door to the deep and beautiful world of complex analysis.